Hello everybody, and today we will continue our discussion of autonomous systems, and we will speak about autonomous systems and stability. What's the problem with the blackboard? Autonomous systems and stability. So we continue to discuss differential equations, autonomous differential equations of the form x prime equals f of x. Okay, and particularly we will discuss two-dimensional autonomous differential equations. This means that all of these are two-dimensional, so x is a two-dimensional vector and f is also two-dimensional vector. And in terms of coordinates, it can be written as x prime equals f1 of xy, y prime equals f2 xy. So the systems will be two-dimensional. But some conclusions will be generalized to n-dimensional case, right? So we will be mostly interested in two-dimensional case, but results will be generalized to n-dimensional case. Okay, so we will discuss phase portraits and phase space. It is more convenient to consider phase portraits in two-space xy plane. So phase portraits and xy plane rather than integral curves and directional fields in txy. So it is more convenient to discuss plane figures than space figures because it is difficult to visualize, right? But if our system is autonomous, then through any point x0, y0 in the phase plane, in the phase space, there is only one trajectory that passes through this point in phase space. And so it is more convenient to discuss phase space, that is two-dimensional space, to make a qualitative analysis of these systems, right? So we will discuss phase portraits. We will continue to discuss phase portraits. And in the preceding lecture, we have discussed linear differential equations of the form x prime equals ax, and we have classified them, right? We tried to find eigenvalues, eigenvectors, and we will give description or classification of all possible phase portraits depending on the eigenvalues. So it is important to consider the cases when these eigenvalues are both real and have the same sign or different signs, and we will get qualitatively different pictures for these cases. And when the eigenvalues are complex and they are complex conjugate, so we will obtain different different phase portraits. So we have obtained a complete classification of all the cases, all the possible cases for two-dimensional spaces. And today I want to discuss nonlinear autonomous differential equations and their linear approximation. So near critical points that correspond to equilibrium solutions, it is possible to linearize this general differential autonomous differential equation and use our classification obtained before. But I want to start with the introduction of very important notions of stability and instability of autonomous differential equations. Okay, and so right, so we will discuss, we will introduce the notion of stability. So suppose x0. So is a vector. Sometimes I will omit the bar above this vector. So suppose x0 is a critical point of our system, two-dimensional differential equation, f prime equals f of x. Critical point means that f of x0 is equal to 0. So I'd like to recall that critical points means this. And so this means that the solution, so x, which is identical to x0, the constant solution, will be a solution of this differential equation. Because if we substitute the constant to the left-hand side, we will get the derivative of a constant, which is 0, and we will get 0 in the right-hand side. So all these critical points are equilibrium solutions or equilibrium orbits. So these critical points correspond to equilibrium solutions. Okay, and I'd like to introduce the notion of stability of our solutions of this general system near critical points or equilibrium solutions. Okay, so this will be definition 1. So a critical point x0, this is a vector, is called stable. Okay, stable. A critical point is called stable if for any epsilon greater than 0 there exists delta greater than 0 such that any solution for any solution with which satisfies any solution x of 0 minus x0. So the norm of x0 minus x0 is less than delta. Okay, any solution which satisfies this condition will also satisfy the following: x of t, the norm of x of t minus x0 is less than epsilon. So geometrically, this means that if we consider a critical point x0, then for any epsilon, a circle of, so I draw a circle of radius epsilon. There exists a circle of radius delta. So this is delta. Usually delta is less than epsilon, or less or equal than epsilon, such that if our solution starts inside, so within the circle of radius delta, then it behaves, it may leave this circle. It may pass outside the first circle, but it can't pass outside the circle of the greater radius epsilon, right? So the behavior is like this, or maybe, so this is delta, this is epsilon, or it may behave as follows. So it starts here, then it goes this way and return to this point, or something like this. So maybe solutions rotate, right? But the main property, so our definition says that if our solution starts sufficiently close to x0, it must stay close to x0 within radius epsilon, right? So if it starts in this circle, so near sufficiently close to x0, it must remain close to x0 within the distance epsilon. So this is the notion of stability. If an orbit is, the critical point of an orbit is not stable, it is called unstable. So otherwise, x0 is called unstable. Okay. Well, so stable, unstable, and the second definition will be about asymptotically stable critical points. Asymptotically stable. Well, so definition number one says that any trajectory which starts near x0 must remain near x0, right? But it must, it is not necessary for that trajectory for the solution to approach x0 as t approach infinity. So x of t may not approach x0 as t approaches infinity, positive infinity. But for asymptotic stability, this condition must be satisfied. Okay, so x0 is asymptotically stable. If x0 is stable, so this is the first requirement, is stable. it must be stable, and if in addition to being stable there exists delta greater than 0, such that for any solution x of t satisfying x of 0 minus x0, so the norm of x of 0 minus x0 less than delta 0, it follows that the limit of x of t as t approaches positive infinity is x0. So this means this definition states that any solution that starts near x0 must remain close to x0, and in addition it must eventually approach x0, right, as t approaches plus infinity, right? So these orbits, so these solutions are not asymptotically stable, but for the asymptotically stable we must have the following. So this is x0, so epsilon delta. If our trajectory starts from the point near x0, it must not only remain inside, so within the circle of radius epsilon, but also it must approach x0 as t approaches infinity. So it must behave like this, right? Like a spiral sink, right? Like spiral sink. Okay. And the second remark, so I will make a remark. Okay, so the notion of asymptotic stability is more rigorous than the notion of stability, right? It is, so this condition is stronger, so asymptotic stability than stability. Because before checking this condition, asymptotic behavior, right, before checking this limit, we must check that our point is stable. So to be asymptotically stable, our critical point must be stable at first. Okay, so the question is, what is your opinion? Is it possible to omit this requirement? So is it true that only this requirement will guarantee, so if the limit of x of t is x0, will it be enough for the point to be asymptotically stable? So will there's this requirement number 2 implies requirement number 1. Is it, so suppose the limit is x0, is it true then that then x0 is stable in the sense of this definition? What is your opinion? Maybe we need not require that x0 is stable. Maybe only the second condition is enough for the point to be, no, yes, no. So the example, maybe I will not write the exact formulas, but qualitatively we may face the following situation when x is a critical point, equilibrium orbit, and well, something like this. So suppose our trajectories will leave x0. So consider trajectories that start from this point, then make a loop, and then return to this point as t approaches infinity. So sorry, t approaches as t approaches positive infinity, we will approach this point x0. But as t approach negative infinity, we will approach this point from the opposite side. And the phase portrait may have this form. Okay, and something like, for example, like this, and the right-hand side, right? So it will be something like this. Well, so for phase portraits of this form, we can see that eventually, so the limit of each trajectory, so ultimately each trajectory will approach x0, right? Because each trajectory goes, so which would start near the point x0. Okay, so I think, okay, any trajectory. So so suppose we have the same behavior on the right, right? So so this condition is satisfied for any trajectory that start near the point x0, right? Near the point x0. But all this, so but x0 is not stable, right? The point x0 is not stable. Since we can't find a delta greater than 0, such that if we start within the circle of radius delta, then we will remain inside some circle of radius epsilon, right? Because you can see that if we start from this point, for example, our trajectory will go outside any circle, right?
Looks like a magnetic field.
Sorry?
Looks like a magnetic field.
Yes, yes. And so to define an asymptotically stable orbit, we should require that x0 is stable. So this must be the first requirement. And then in addition, we must have this condition. Okay, well, and now I'd like to consider an example of the oscillating pendulum, and this physical example will explain the notions of stability, instability, and asymptotic stability. And so now we will consider the oscillating pendulum. Oscillating. Okay, this is a physical model, and So the description of this is the following. So consider the origin, and we will consider the pendulum. So we consider a mass M, attached to the rod, and this rod is supported at the origin, at the other end. So this is mass. So I think I will draw another figure. So let it be the origin. Okay, this is the mass M. This is the rod. It is rigid but weightless. Okay, and the other end of this rod is supported at the origin. This mass can rotate, so it may rotate freely in the plane. Okay, there are forces that act to our mass. The first force is a gravitational force. It is mg. This is a gravitational force. Okay, to describe the position and to motion of this pendulum, we will introduce the angle between downward vertical direction, and theta will be positive. So if we move clockwise, okay, so counterclockwise, right, in the plane. So theta is the angle between this vertical direction and our rod. Okay. So we should take into account also a damping force. So first, the gravitational force, which is acting on this mass. Okay, and damping force. Okay, damping force acts in the direction opposite to the motion of this mass. Okay, so if our mass is moving this way, then so this is, suppose this is the direction of motion of our pendulum, of our mass, then the damping force will act in the opposite direction, and the absolute value of this force is equal to c times d theta over dt. This is the damping force. So L is the length. Sorry? Mechanics, yes, but so how can I explain? Okay, have you studied the analytic, maybe the mechanics or analytic mechanics, right? So you are familiar with this, right? Are you familiar with the equation of motion of the oscillating pendulum? No?
I forgot it.
Forgot, yes, right. So from the principle of angular momentum, we can write the following equation. So the equation, I will only write it, but I don't want to discuss the okay. Right. So the well, minus. So the momentum. So I must multiply this by so mg, so the projection to this direction, this is theta, and so it will be mg multiplied by L, by the length of this, and sine theta, right, and minus, and this damping force multiplied by L also, right, d theta over dt. Right. Well, now let's divide by, so divide. Next, in what follows, we will analyze this equation, right? So if we divide by both parts by ml squared, we will get the following: d2 theta over dt squared. So plus, let it be plus mg divided by, so it will be g over L, or maybe we will start with this. So c divided by ml d theta over dt plus m divided by, so g by L sine theta is equal to 0, right? So usually, so these are two constants. Usually this constant is denoted by gamma, and this is omega squared, and so we get the following equation: two dots, or maybe two primes. I don't know what is better. Times. So dot is better. Right. Sine theta equals 0. Right. So this is the equation. And we will discuss this later, try to linearize it. But first of all, let's discuss stable critical points, stable equilibrium, unstable equilibrium, and discuss asymptotic stability. Okay, so by definition, first of all, so to find, to discuss, before we discuss stability and instability, we must find the zeros of the right-hand part, right? But before this, we should rewrite this as the first order differential equation, right? So this is the second order differential equation. We must rewrite this as the first order differential equation. To do this, we should introduce new variables. Let x be equal to theta and y is theta dot. Then, sorry?
Will we have a system of
System, yes, but now we're discussing the system of differential equations. So I told I start my lecture with the phrase that we consider two-dimensional differential equation, right? So this is a vector equation. X prime equals f of x is a vector equation. We will get the system of equations, of course, or we may consider it as one vector equation, one first-order vector equation. Yes, so if we introduce these variables, we will get the following system. X prime is equal to y. And y prime equals, so y prime is equal to minus gamma y minus omega squared sine x. And now we're speaking about this system of first-order differential equations. So to analyze equilibrium positions, to analyze stability, first we need to find equilibrium positions, right? Okay, so to do this, we must equate this right-hand side to 0, right? We must solve these equations. Y equals 0 and minus gamma y minus omega squared sine x equals 0. solving this, so y is 0, we will substitute 0 for y. And so this is the same as y equals 0 and sine x equals 0, right? So we obtain the following positions. X equals pi n, right, where n is integer, and y equals 0.
Wait, can you explain one more time why do you say y is equal to 0?
Because we need to find the critical point. So we discuss the stability of a critical point. We need a critical point and then discuss a stability. So it must be an equilibrium position, an equilibrium point, right? In equilibrium orbit.
It doesn't sound true because at y is equal to 0, the x is always the maximum or minimum.
Yes, but you speak about let's consider this pendulum, and if it is oscillating in this way, it goes through this position, but its x coordinate, so theta is 0, but at this position y prime is not 0, right? Yes, and the same is yes, it is maximum, right? But for the critical, for the equilibrium, so if this pendulum is at rest in this position, then x is 0 and y is 0. Then both x and y are 0. But when we discuss this oscillation, we discuss something like, so this point is stable, but we move around this table near this point, and so y may be non-zero and x also may be non-zero near this position when we are oscillating. But if so in ideal situation, so the pendulum will oscillate indefinitely. But if we take into account the damping force, then the amplitude will decrease gradually, right? And the velocity will also decrease, right? And approach this position. Both the x coordinate and the velocity, right? So the speed of the pendulum will also approach 0, right? If you may imagine this, right? Okay, right. So this is the equilibrium position. And as I have already told, okay, we can see intuitively, we can see that, so if this is the origin, then this low equilibrium position is stable, right? And it is asymptotically stable, right? Okay, because if we start, if we displace maybe, so this is the equilibrium position. If the pendulum is at rest, then both x and y are 0, and it is at rest. And if we displace slightly this pendulum, then it will start to oscillate back and forth, right, in this way. Okay, with a decreasing amplitude, right? And eventually it will approach this equilibrium position, right? So theta will approach 0, and theta dot will approach 0 also, as t approach positive infinity, right? Well, and so this position is asymptotically stable. Okay, but if and this is the first case. So if we consider the same position, but if, for example, we consider an ideal case, an ideal situation where when there are no damping force, this coefficient is 0. This, of course, an ideal situation, because in practice, physically, it is impossible to reach that C is 0, right? It is impossible, of course. But in ideal situation, if C equals gamma equals 0, then so this pendulum will oscillate indefinitely, and it will not approach this equilibrium position, right? And so in this case, when gamma is not 0, this position is asymptotically stable. But in this situation, it is only stable but not asymptotically stable. Stable because our orbit will stay near the equilibrium position for a while, right? And it will not go away from this neighborhood, but it will not approach this position asymptotically, right? So it is stable, but not asymptotically stable. Okay, and the last, so maybe it's enough space for this. So this position, so this is our mass, and this vertical position is an unstable equilibrium, right? This is an unstable equilibrium, because if we displace this mass a little, then it will fall, right? And it will oscillate in this way, and after this, it will approach this stable position, asymptotically stable position, right? So this position is unstable and this position is stable. Well, so this is a physical model. This is to clarify the definitions, these three definitions of stable, unstable, and asymptotically stable point. Linear approximation to nonlinear systems. We will discuss how is it possible to approximate okay, linear approximation. By what?
You mean sine theta is equal to theta?
Yes, yes. So this is a linear approximation, of course. Sine is approximated by theta. Sine theta is approximated by theta. If theta is small. So something like this will be done generally. Linear approximation, right, to nonlinear systems. Okay. Near critical point, near the point of equilibrium, it is very fruitful to find the linear approximation to our differential equation, approximated by some linear system near critical point. And I state that in this case, the pattern of trajectories in the phase space will resemble the trajectories in the linearized system. And so it is very important to be able to linearize this system, to approximate this equation by a linear equation. in what follows, we assume that x0 is the origin. It's better to speak about the equilibrium point at the origin. If not, we can make a change of variables. If not, we can introduce a new variable u, which is equal to x minus x0. So this is a vector. And by this change of variable, we will reduce our system to that of x minus. So it will be u plus x0. And our critical point x0 will move to 0, to the origin. So in what follows, we will assume, without loss of generality, that our critical point is the origin. Okay. And okay, we will start with them. So we want to replace our nonlinear differential equation by equation of the form A times x, where A is the matrix. Okay, and we will start with the definition. Okay, it will be here. Okay, suppose that we represent, so we rewrite our function f of x as a times x plus g of x, where A is a matrix. In our case, A is a 2 by 2 matrix, but this, of course, can be generalized to the n-dimensional case. Okay, and suppose three conditions are satisfied. Then suppose that first 0, so x0 equals 0, is an isolated critical point. Isolated critical point. This means that there exists a circle centered at the origin, such that there are no other critical points inside this circle, right? Isolated critical point. The next requirement is that the determinant of A is not 0. So A is not degenerate. And so this means that okay, so it follows that x equals 0, the same, of course, is an isolated critical point also for the linearized differential equation AX. And the last requirement is that G of x is of class C1. And G of x, that the norm of G of x over the norm of x approaches 0 as x approaches 0. So this means that G of x, the function G of x, is small in comparison with x, right? With x. And if these three requirements are satisfied, then x prime. So then the system x prime equals f of x is called a locally linear system. Of differential equations, locally linear system of differential equations. And this linear system is called the linear system associated with our given original nonlinear system. So I will rewrite it maybe. So I will rewrite it in the following way. So we have started with the nonlinear system f of x, with the equilibrium solution, which is equal to the which coincide with the origin, and the linearized system will be given by x prime equals ax with this equation. Okay, let's consider an example. Let it be this. So I will use this part of the blackboard. So example. I will consider the following the system of differential equations. Differential equation given by I will rewrite it later. Let it be given. I will write it in the form x prime equals x minus x squared minus xy, y prime equals 0.5 y minus 0.75 xy minus 0.25 y squared. Okay. And the task is to check whether this system is locally linear near. So is it locally linear? Near the origin. Let's to find, so first of all, we should rewrite it in this form. So to find the linear part and the other terms. So from this system, it is clear that this will give us the linear part. So I will first rewrite this system as the product of the matrix by the vector xy and minus the vector x squared plus xy 0.75 xy plus 25y squared. Okay, and I must check that x0 is an isolated critical point. So first of all, we should check that there are no other critical points in the neighborhood of 0, 0. How to do this? So the first step is to check that this is then an isolated critical point. Okay. Now, so I should equate this to 0. So if x is not 0, then I will divide this equation by x, and I will get, so we're near the origin, and so x is not 0 or y is not 0. If we assume that x is not 0 and divide by x, we will get the following. So from the second equation we get, if we multiply it by 4, we will get y times 2 minus 3x minus y equals 0. Okay, so maybe I will write it in this way, and so it is clear that there are how many points? So 0, 0, or this is 0 together with this, right? So the critical points are 0, 0, and if we equate to 0x and this expression, we will get the point 0, 2. If y is 0 and this is 0, then we will get 1, 0. And at last we will obtain, so the last point will be, so if we equate to 0 this part, we will get the following. So y equals 1 minus x, and substituted here we will get 2 minus 3x minus 1 plus x is 0, and we will get x, which is 1/2, and y is 1/2. So the last point is 1/2, 1/2. So we have 4 critical points, and so this proves that 0, 0 is an isolated critical point. So the first requirement is satisfied. Now requirement number 2. So the determinant of the matrix. So we need to know the determinant of this matrix, but it is not 0.5, it is non-zero. And the last requirement says that so this part must be small in comparison to the norm of x and y. So the norm of x is equal to the root of x squared plus y squared. Let it be rho. And I want to prove that x squared plus xy divided by rho approaches the norm of this, approaches 0. So the absolute value approaches 0. And and we need to prove that this part approaches 0 also. 3/4 xy plus 1/4 y squared over rho approaches 0. So this can be easily done by introducing the polar coordinates rho and theta. If we rewrite this in terms of polar coordinates, x is equal to rho cos theta, y equals rho sine theta. And if we introduce these expressions into our formulas, we will get the following: rho squared cos squared theta plus rho squared cos theta sine theta over rho. So it must be rho also. We can rewrite it as rho times cos squared theta plus cos theta times sine theta. It is less than 2 rho, which approaches 0. So we have proved that this approaches 0 as rho approaches 0. So this component is small in comparison with the norm of x, and by them, so likewise can be proved that the second term, the second component, is also small with respect to the norm of x. And so this proves number 3, part number 3. Okay, maybe I will formulate them. So the theorem, and after this we will stop our consideration of. So we will finish our lecture after I will formulate theorem. So if the function f is of class C2, and if the Jacobian, so the determinant of the Jacobian matrix, so the determinant of the Jacobian matrix is non-zero at x equals 0 at the origin. Then our system is locally linear. So the proof of this theorem, so I will omit the proof, but it follows from the Taylor expansion of the function f of x near the origin. And from this theorem we can obtain the formula for A. So if we have a differential equation such that f is of class C2, then we can find A, the matrix for the linearized system, which is equal to the Jacobian matrix. So it is equal to df1 over dx, df1 over dy, df2 over dy, df2, so over dx, dy. So A is the Jacobian matrix. Okay, well, so and maybe a few words about the stability. So we will need this, and after this, during the seminar, we will try to linearize some nonlinear systems and try to make some conclusion about their phase portraits. Okay, so about the stability. Okay, stability of locally linear systems. So the statement is if all okay, so all the real parts real parts of eigenvalues of the linearized system A, of the linearized matrix, of the Jacobian matrix, are less than 0, then our linearized system and the corresponding nonlinear system will be locally, so will be asymptotically stable. And if there exists an eigenvalue for which the real part is greater than 0, so real part is greater than 0, then our linear system and the corresponding associated nonlinear system is unstable. And in what follows, we will use these two facts, and we will use these two theorems during our seminar. We will apply them to analyze the particular nonlinear systems of differential equations. We will linearize them and we will discuss the patterns of their behavior of the trajectory. Okay, now we will have a break for 10 minutes. Thank you for your attention, and this is the end of our lecture.